Hello everyone. In this video, I am going to show you how to conduct a chi-squared goodness of fit test for a non-uniform distribution. So a distribution that is specific but non-uniform. So in this example, the owner of a mail order catalog would like to compare her sales with the geographic distribution of the population. She wants to see if the distribution of her sales corresponds with the distribution of the population. According to the United States Bureau of Census, 21% of the population lives in the Northeast, 24% in the Midwest, 35% in the South, and 20% in the West. So we want to test that the distribution follows these percentages specifically. So for the null hypothesis, I'm going to write this as P1 equals 21% or 0.21. P2 equals 0.24. P3 equals 0.35. And P4 equals 0.20. So in the null hypothesis, we specify each of the proportions. So here we're specifying 4 different proportions, and we want to test that each of these proportions is met. For the alternative, all we need is any one of these not to be right. So we can say at least one of the proportions is different from stated. That's just easier to say. At least one of these proportions here is different. Per usual, I am using an alpha of 0.025 to correspond to 1/tail of a 95% confidence interval. So when we do chi-squared tests, we are always comparing observed frequencies with expected frequencies. And the data we're given are the observed frequencies. So our regions here, Northeast, Midwest, South, and West. Okay, region is our variable, and these are the different possible values of the variable. So this is our qualitative data. Here are the observed frequencies, 68, 104, 155, 73, a total of 400. And the expected percentages, I put these here to make computing the expected frequencies easier. Because if this is our expected percentage, then we would expect to get frequencies that correspond to 21% of the 400 should be here, 24% of the 400 here, 35% of the 400 for the South, and 20% of the 400 for the West. So what are these values? Well, 21% of 400, I am going to do F4 to get dollar signs for 400 because I want this to stay, but the percentages will change as I copy the formula. So the expected frequency is 84. The observed was 68. It's hard to say if that difference is statistically significant or not. And then we need to see the others as well. Lots of times what I think is significant is not. Sometimes what I think is not significant is. You really need to crunch the numbers. Of course, a lot of it depends on the sample size here. But let's copy this formula down. 96 compared to 104. That's a lot closer than 68 and 84. 155, 140, 73, 80. Just to make sure we have everything right, we should get a sum of 400, and we do. So now to compute the chi-squared test statistic, we need to find the differences as positive ratios between the observed and expected frequencies. O here stands for the observed frequency, and E for the expected frequency. We take the difference between these, because we want to see if the difference is statistically significant or likely due to random sampling error. We want these differences, though, to be positive, so we square them. And we want it as a ratio to the expected, how far off relative to the expected, so we divide by the expected. So let's compute a formula for this. So equals, open parenthesis, my first observed in B17 minus my first expected in D17, close the parenthesis, square it, and then divide it by the expected frequency. So here's our formula. Enter. I will copy it down. These individual numbers don't look too big, and when we sum them up, that doesn't seem too big either, 5.9. All right, so that doesn't seem too big. My intuition, we'll see if it is right or not, my intuition is that we will not reject the null hypothesis, that we can support these percentages, but let's crunch the numbers to be certain. Degrees of freedom is one less than the number of categories. So we have 1, 2, 3, 4 categories, so our degrees of freedom is simply 3. And now we need to find the p-value using a chi-squared distribution. So let's review the chi-squared distribution. A chi-squared distribution is a right-skewed distribution. So let us sketch here. I will sketch here for us a right-skewed distribution. Since it's a distribution of these squared ratios here, so it will always be positive. And as you get further to the right, it gets larger. So we always have positive values that get bigger as we move to the right. These are going to always be right-tailed tests. We want to find the area in the tail defined by our test statistic here, 0.59. So I will just arbitrarily draw a chi-squared, a line here for our chi-squared test statistic. Chi is an uppercase Greek letter, so chi-squared, and our chi-squared is 5.9. And then we want to find the area of the tail that it defines. So it's always a right tail, always a right-tailed test. So we need to find the probability of being at least 5.9, the probability of getting a test statistic. What's the probability that we get a test statistic that is 5.9 or greater? Under the assumption that of this specific distribution. If this value is high, as in greater than our confidence interval, our alpha, 0.025, then it's likely due to random sampling error, and we can support the null hypothesis. We can support that this is likely the distribution. If, however, this is a small value, that the probability of getting a 5.9 or greater is small, where small is less than the alpha 0.025, then we conclude that these differences are statistically significant and therefore likely do not follow this distribution. So let's find out what that p-value is. So the p-value, chi-squared distribution, and it's a right-tailed test. So chi-squared dis.rt, the x input is our chi-squared test statistic, comma, then we need the degrees of freedom. That's it, just those two inputs. Close the parentheses and, not too surprising, a large p-value. So what we have here then is that the p-value is 0.115 rounded off. It's about 11.5%, definitely bigger than 0.025 or 2.5%. So our conclusion then, let us write this up, our conclusion. starting off with the fact that the p-value is greater than alpha. So we fail to reject the null hypothesis. That means we support the assumed distribution. So the sample data support that the distribution is as stated. All right. So that means the differences between the observed and expected frequencies were likely due to random sampling error and not statistically significant. So the differences between the observed and expected frequencies is likely due to random sampling error and are not statistically significant. All right, and what type of error might have been made? Well, we failed to reject H naught. So since the null hypothesis is supported, we have a possible type 2 error because it could be that the null hypothesis is actually wrong, although we supported it. I hope you found this video useful. I thank you again for watching.